Welcome to a special edition of Chemistry 115. I'm going to show you two Lewis dot structures, one for sulfur trioxide and another for phosphate. And I want to talk about how they are both similar and different and how the rules of G. N. Lewis way back in the day influence how we draw Lewis dot structures today. We'll draw SO3 in the two ways that I showed earlier on today in class. With this structure, I have 4 atoms that each have 6 valence electrons. That gives us 24 total valence electrons. The skeleton structure will begin this way. Sulfur, the least electronegative atom, becomes the hub, and I place all electrons that remain around those oxygens. That's now 24 completely. The structure isn't done though because sulfur's octet is not filled. I can complete it by taking any one of the lone pairs on these external atoms and move it into a pi bond. That would give me this structure. This structure now has all atoms with octets filled. If I give formal charges now, that oxygen is 0. Each of these 2 oxygens is a -1. They do have 7, but they should only have 6. The sulfur in the middle should have 6, but it does have 4. It wants 2 more negative charges, meaning that it is overall 2+ as its formal charge. This compound can be drawn this way. I think it's totally fine. I think it's probably the most acceptable structure. But given that sulfur is an atom that can invoke hypervalency, as in it can use more than the typical valence pictured on the periodic table, G. N. Lewis and others like him, other chemistry professors, have said the 2+ charge and the 2 oxygens being negative, well, we have a lot of formal charges. Maybe we can continue to share electrons to reduce those overall formal charges. And it does happen to be so that if I take another lone pair here, maybe I'll do it with this color, and move it here, I get a new structure. Draw that down this way. Sulfur, double bonded to the top oxygen still, but now double bonded to the side oxygen on the right. This last oxygen still has all 3 lone pairs. Formal charges for this oxygen and that oxygen are 0. This oxygen still a -1. That sulfur, though, it should have 6. It does have 1, 2, 3, 4, 5. It's still lacking 1 electron, but now its formal charge is closer to 0. And there are now only 2 atoms with formal charges, with one last movement of a pair of electrons. I can neutralize all formal charges and leave this structure as another accepted Lewis dot structure. Both of these two would get full credit in this class, but let me show you where something is. Let me show you a subtle rule, and I can demonstrate that with phosphate, PO4 3-. With this structure, I've got 4 oxygens, each contributing 6 electrons. I've got a phosphorus that contributes 5 valence electrons, and then there's a surplus of 3 additional electrons. Overall, 24, 29, 32 total electrons. I'm going to put phosphorus at the center because it is the least electronegative atom. 1, 2, 3, 4 oxygens around the periphery. I only have 8 electrons in here. I need 24 more. It turns out it is exactly the right amount to give every oxygen 3 lone pairs. At this point, all octets are filled, phosphorus and the 4 oxygens. I'll go ahead and do formal charges now. Each oxygen should have only 6, but it does have 7, one more negative charge. Given that the overall charge is 3 minus, I know that phosphorus needs to balance out those 4 minuses. It should have 5 electrons, but it only has 1, 2, 3, 4. It's lacking 1 electron. It has a positive charge. The net charge is still 3 minus. That way I know that I've done my structure right and I put in the right numbers of electrons. However, while this structure to me is perfectly acceptable, it is actually supported by all the evidence that we have related to computational and spectroscopic evidence. This is not the kind of structure that you will find. Given that phosphorus is right next to sulfur in the periodic table, it too can be hypervalent. So what we could imagine is taking a pair of electrons, maybe over here, and sharing it with the phosphorus. That phosphorus atom would be double bonded to the oxygen on the right-hand side, and if I leave all the other oxygens alone, I go back and I calculate formal charge. This atom is 0 now. While the remaining oxygens are unchanged, there's still 1 minus. That phosphorus should have 5, and it does have 1, 2, 3, 4, 5. It's neutral. I have, by doing this action, creating a second bond, a pi bond between the phosphorus and oxygen, I've neutralized their formal charges. This structure will always have a 3 minus somewhere, but you could ask yourself, if this oxygen can make a second bond with phosphorus, why can't they all? Let's go ahead and do that. I'm just going to skip straight to the final structure where all of these oxygens would be sharing their negative charge with phosphorus. Presumably, this could happen. Phosphorus has access to d orbitals. It could have enough to make all of these bonds along with its s and p set. But let's now do formal charges. Oxygens are all going to be 0. But given that all of those oxygens have a 0 formal charge and the molecule still needs to have an overall 3 minus, that 3 minus must be located on the phosphorus atom. In fact, it should have 5, but it does have 1, 2, 3, 4, 5, 6, 7, 8. It has 3 more electrons than it needs. That is a 3 minus formal charge on phosphorus. And here's the big issue with this. That phosphorus is the least electronegative atom in the molecule, and yet it is shouldering all of the negative charge. It stands to reason that oxygen would be the better location for those negative charges. And so this is not the best structure. What G.N. Lewis says, and what is common about both of these eventual structures, if I can get my papers all together, G.N. Lewis says that you are allowed to take the central atom hypervalent until formal charges have become 0 for that central atom. This is the point where you need to stop on phosphate. With sulfur, you're allowed to go until you get to 0 formal charge, which just happens to coincide with all of the oxygens double bonded. So this structure and this structure are the accepted structures for phosphate, and this structure and that structure are the accepted ones for sulfur trioxide. That's it. Enjoy.